All right, let's jump right in. Today, we're talking about something kinda invisible but absolutely essential to our digital lives. We're talking about axioms. Think of them as the silent, powerful rules running in the background of, well, pretty much everything, from your internet connection to even how we think about digital fairness.
So you might be thinking, ancient rules? What's that got to do with my Wi-Fi? And honestly, it's a fair question. But there is a direct line from these old school principles of logic to the very network that's bringing this explainer to you right now. So what's the connection? It all starts with this really powerful idea called the axiomatic method. And here's the big idea. Instead of trying to tackle some massive, super complicated system all at once, you start with just a handful of simple, undeniable truths. These are your axioms. From that rock-solid foundation, you can logically build up these incredibly complex and, most importantly, reliable systems. It's like having the ultimate set of building blocks for knowledge.
Okay, so let's make this real with our first example. Before we can even begin to figure out how well a network is performing, we all have to agree on how to talk about things like chance and uncertainty. And that, my friends, is where probability comes into play.
I mean, just imagine trying to play a game where nobody agrees on the rules. It would be total chaos, right? Well, it's the exact same thing for network analysis. If engineers don't have a shared, fundamental understanding of probability, there's no way they can measure performance or predict problems. Now, here's the cool part. This quote points directly to the solution. Researchers came up with an axiomatic introduction of probability. In other words, they laid down the fundamental agreed-upon rules of the game. That way, any analysis from anyone, anywhere is built on the exact same solid ground. And this axiomatic approach is it's everything. It creates that common language, it gives us the basic tools to measure likelihood, and crucially, it makes sure that when two different engineers look at the same network, they get consistent, comparable results. Without that, you'd have digital chaos. This is literally the foundation of trust for our global networks. All right, so let's see how this builds into something even more practical. See, axioms aren't just these abstract philosophical rules. They can actually work like a recipe for dealing with incredibly complex problems. I want you to picture rush hour traffic on a major highway. But instead of cars, it's data packets. Heavy network traffic can look completely random, totally unpredictable. So how on earth do engineers manage it and make sure your connection doesn't just, drop? They need a reliable model. They need a recipe. And there it is, the axiomatic recipe. And get this, that's not just a metaphor I'm using. That's the actual term researchers use. They use a set of axioms, these foundational rules, to define exactly how a network's servers should behave when they're under a lot of stress. It's a step-by-step guide that comes from a few simple truths. So here's how that recipe actually works. First, they use those axioms to lay out the basic behavior of the servers. From there, they create this really clever mathematical tool called a drift function. You can think of it like a traffic cop for data. It predicts where things are going to get bunched up and helps steer the data smoothly. And that function becomes the key to managing the flow even when traffic is insane. A simple recipe for a crazy complex problem. Okay, now, for what I think is the most mind-blowing application of all of this, using these cold, hard mathematical rules to define something as human and, subjective as fairness. We all learn this rule as kids, right? The first person in line gets the first turn. It seems simple, but in a really complex data network, is that actually the most efficient or even the fairest way to do things? I mean, what if a tiny, super quick request gets stuck waiting behind some massive hours-long download? Is that fair? So the simple, naive approach just focuses on the order, but the axiomatic approach asks a much, much deeper question. Can we actually develop a mathematical measure of fairness itself? Can we create a tool that tells us objectively just how fair a system really is? And that is exactly what researchers are doing. They're using an axiomatic approach to literally build a mathematical definition of fairness for queuing systems, which is really just a fancy term for any system where things, or in this case, data packets, have to wait their turn in a line. And this is the brilliant result. The axiomatic approach gives us a yardstick, the variance of the waiting time. So if wait times are all over the map, some are super short, some are incredibly long, the variance is high, and that means the system is unpredictable. You could say it's unfair. But if pretty much everyone's wait time is about the same, the variance is low. It's predictable. It's fair. Math just gave us a definition for fairness. How cool is that? So let's pull all these threads together. We've seen how axioms can give us a common language, a practical recipe, and even something like a mathematical compass for fairness in our digital systems. But why is this so important?
This table really sums it up perfectly. For probability, axioms give us that common ground we need. For modeling complex systems, they give us a recipe to manage the chaos. And for something like queuing theory, they let us translate a deeply human idea, fairness, into cold, hard, objective math. Ultimately, what this all comes down to is that axioms are the bedrock of trust in our digital world. They provide the kind of rigor and clarity that lets us build these massive, unbelievably intricate systems and actually have confidence that they're going to work reliably, efficiently, and yeah, even fairly. And that kind of leaves us with one final thought. We've seen how just a few simple, self-evident truths can bring predictable order to the chaos of our digital world. So it really makes you wonder, right? What other complex, messy systems in our lives, maybe in economics, in society, or even in our own thinking, could be better understood if we just stopped for a minute and first agreed on the axioms?